Hi, my name is Joe Jacob. I'm an electrical engineer with Padge LLC. This is the first of several videos about harmonics. Today, I want to introduce harmonics by describing what they are and giving a simple example. The next video will describe where they come from in an electrical system. Fundamental frequency of voltage and current in North America is 60 hertz. A harmonic is simply a whole number variation of that fundamental frequency. So, for example, the third harmonic is 3 times 60 hertz, which is 180 hertz. Let's look at an example voltage waveform. Our pure 60 hertz voltage is going to be 480 volts AC RMS. RMS means root mean square. I'm not going to talk about root mean square here, but I encourage you to look that up. 480 volts AC RMS has a peak voltage of 678.8 volts. This waveform looks like this. Notice it goes up to 678.8 volts on a time value of 4.16 milliseconds. It has a zero crossing at 8 2/3 milliseconds. It goes down to negative 678.8 volts at 12.5 milliseconds, and then it completes the entire period after 16 2/3 milliseconds. I have two periods shown here. A period is one complete cycle. We're going to look at three harmonics, which are extremely common ones. We're going to look at the fifth harmonic, which will be 3% of our fundamental. We're going to look at the seventh harmonic, which will be 2% of our fundamental. And we're going to look at the 11th harmonic, which will be 1% of our fundamental. These are just arbitrary values that I've picked for our example. They're quite representative of an electrical system with low harmonics. Let's start with the fifth harmonic. I have the fundamental still in at 480 volts AC RMS, and I have shown the fifth in at 3% of that, or 14.4 volts RMS. Notice how for one period at 60 hertz, this 14.4 volt waveform will have 5 periods. Now let's look at the 7th and 11th, which we're saying are 2% of the fundamental and 1% of the fundamental respectively. This is a plot of those four waveforms. Now, I have kept the waveforms separate, but harmonics are additive to the fundamental waveform. Sometimes you can add two numbers and they result in a bigger number. Sometimes you can add two numbers and the result is a smaller number. 1 plus 1 is 2. 1 plus -1 is 0. These waveforms are trigonometric. They can also be larger ones or smaller ones when added. I'm not going to get into how to add trigonometric sine waves here, but I encourage you to also look that up. This waveform is what they look like when they're added all together. Doesn't this look strange? Notice the peak is no longer 678.8 volts, but is now 680 volts. We as humans will struggle to make sense of a waveform like this, so we like to view it differently. There's a technique called the fast Fourier transform, FFT, that helps break down complex waveforms to make it easier for us to view as humans. I'm not going to get into that here, so I'll make it simple. Please look up fast Fourier transform, often called FFT, if you're interested. Our example had 3% on the fifth harmonic, 2% on the seventh harmonic, and 1% on the 11th harmonic. The way we like to view it is like this plot. This makes it so much easier for us to see. I have one final thing I need to show in this introductory video, and that is how to calculate total harmonic distortion. The formula is quite simple. We add the square of all the harmonics and then take the square root of that sum. So, for this example, the sum of 3% squared, 2% squared, and 1% squared is 0.0014. The square root of 0.0014 is 0.0374, or 3.74%. IEEE 519 requires the THD-V to be less than 5% of the point of common coupling, and our simple example is compliant. The next video will talk about how harmonics are created. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at Padge.org, that's Padge.org, if you need anything on this topic or others.